The talk of Professor Yao is spectral statistics of random D-regular graphs. So please.
It's on now? Yeah, I think now it's on, right? Okay, good. Yeah, I would like to thank the organizer for the invitation and to give this talk here. Um, so I'm very so the first thing is I gave this talk just the first time I gave this talk is about 1 month ago, but then I see in the audience already somebody was already in the talk, and I have to say that there's no new results in this 1 month, and so just to we set the expectation correctly. And so, all right, so this is a joint work with Jiaoyang, Huang, and also with Theo, McKenzie. So it's about special statistics of random D-regular graph. I mean, it's a problem we work on and off for about a bit less than 10 years, and so. Ooh, cool. Oh, no, I don't think this is what I want. Um, can we go back to full screen? I, um, okay, I think. Oh, all right, okay. I think it's this. Yeah. Oh, yeah. It's just a bit delayed. That's it. Okay. So, so this is the outline what I'm going to say, and the question is about spectral statistics of random D-regular graph. And then I would say the eigenvalues and the rigidity, and then some idea about the proof, and finally say something about edge universalities. Okay. So, so we start from the first one. So let me give you the definition of random D-regular graphs. And so there's a little bit. Some people. So I just said the convention correctly, and so the convention I use is now you take a random graph, and whenever there's an edge between two vertices, and then you set it 1. Otherwise, if there's no vertex, say 0. Okay, but then the matrix itself, and the matrix itself is it's H, and H is this adjacency matrices divided by square root d minus 1. And I divide by square root d minus 1, and that's because I want this to be compared with this Gaussian ensemble naturally, and so this is the right scale. But you don't have to worry; it's just some normalizations. And now you denote the eigenvalue by lambda 1 bigger than lambda 2 and bigger than lambda n. And the first eigenvalue, it's you set the eigenvector is 1, 1, 1, 1, 1, and then you can compute it's just d over square root d minus 1. It's obvious. So the first one is obviously known. Now the random D-regular graph. So this matrix, of course, is highly correlated because you know that every column, if you sum up, is a D, and so it's a highly correlated matrix. And so now, as a comparison, the earliest random graph, I use the G of n. Usually it's a GMP, but now I just directly denote P by D over N. And here, the reason I use this notation is because I want to use this compare with random D-regular graph. So usually it's a GMP, but now I just write P as N over D, D over N, and that's it. All right, so you also normalize correctly, and the normalization is the mean is 0, and the variance is 1 over N. And so, I mean, you have to make some constant subtraction, otherwise the mean is not 0, but but this constant subtraction is quite trivial, so let's not worry about it. It's mean zeroing variance 1 over n. All right, now so now the main reason is we are interested in the expander graph, and actually I just came from this Peter Starnock's birthday meeting, and he has there's the full day talking about expander graph, and this is something. A graph has a very strong connectivity properties, and then there are many applications in mathematics and in computer science. They are looking for this kind of object. So the famous work in the old days there's a work by Elon and Bopana, and they proved that the second eigenvalue is bigger than 2 minus constant divided by diameter of G. And the reason you get 2 here, this is 2 is I mean this because of normalization. You can think about it, just normalize things to 2, and so don't worry about 2 is you'll find out 2 later on. Now as the diameter goes to 0, so you know the lambda 2 in limit is bigger than 2. And now the expander graph. This is of course there are lots of connections, but one very common one is a connection with the Cheeger's constant, and Cheeger constant is defined to be the number of edges divided by the size of the components, and the connection is the Cheeger constant is bounded by the spectral gap. This lambda 1 minus lambda 2. There's some two-sided inequality. This by now is a classic work, and so we are not going to look. I mentioned it's just there's some connections, and not really. We are not going to use any of these. So our motivation really is this paper by Lubetzky and Phillips and Sarnak, and this turned out to be the most cited paper of Sarnak. And so the question is a connected d-regular graph on vertices. Now we call it a Ramanujan graph if lambda I, besides the first one, because we know the first one is already 1, everything else is less than 2, this is called Ramanujan graph. So now the Ramanujan graph is the graph has the best possible, this is best possible spectral expander. And so in the paper 1988, they made a construction of Ramanujan graphs. And this is for the case of it's a D is P plus 1 and P is a prime mod 4. And later on is Marcus Spielman and Srivastava. They construct this for the bipartite case, and but the proof is about existence. It's not really it's not really for okay. All right. So now. Oops, sorry. Do I? All right. So now let's go back to random d-regular graph. So all the previous what I say is about motivation. You can just if you don't know, don't follow what I say too much. Just you can forget about it. Right? Just think about we have a random graph, and you want to understand the eigenvalues and the eigenvectors. And so the eigenvalue distribution of random d-regular graph for any d fixed is given by this Kesten-McKay law. So if we look at this Kesten-McKay, you will see that there are 2 years when the d is, look at the d equal to 3. So this red line is very different from the semicircle. The semicircle is a d equal to 200. It's d equal to infinity. You can see that d equal to infinity, the prefactor d over d minus 1 minus the square x squared divided by d will all disappear. It just becomes 1. And so you just get the semicircle. So this was the classical work by Kesten and by McKay. And I have to say that in this convergence, the first eigenvalue disappear because you are taking the weak limit. So one eigenvalue will just disappear. And so it's not, it does not show in this picture. And now the Kesten-McKay law becomes, so the last sentence I already said, Kesten-McKay law becomes semicircle law. All right, now there's a numerical study, and actually the Sanak started to talk about it in 2004, and he asked his student and to do some simulations. And the simulation find the second eigenvalue subtract 2, and in addition, there's a constant shift. There's a constant C of D, and after the subtraction, this will convert to the Tracy-Widom law. And so the simulation is given by these two graphs. And actually, I just copied this from somebody's talk, and so it's not a simulation. This, in principle, is the one in 2006 they did a simulation, and I think more recently, it seems this picture is quite correct, even though it was done a long time ago. But still, in general, you believe this picture is correct. Now, the Tracy-Widom law is the one that you forget about all the metric elements are Gaussian. So it is random deregular, and then it will converge to something, and there's no correlation, and everything is Gaussian. So that's the assertion. And the assertion that it's you even rescale by n to the 2/3 after subtracting constant, it becomes the Gaussian case. All right. So this was this conjecture. So this was because this Normalized graph it's a popular problem. And so there was a proof in 2004, and then later on it's improved. It's a new proof in 2015, and now there are also some other proofs. And so for fixed d bigger than or equal to 3, this lambda 2 is a 2 plus log n divided by, So there are there's really some error bound, even though it's a log. Okay, so this was, and this is a classical work, and then recently there are many. It seems that some of these methods are useful in random geometry questions, and so. But I don't know much about it, so I don't think I will be able to tell you much about this. Now the result we have is the following. So you take the Kesten-McKay law, and so yes, the Kesten-McKay. So here I use the rho of d. You fix anything bigger than or equal to 3. And then this rho of d is the Kesten-McKay law for d fixed. And now you compute the classical location. So what's the meaning of classical location? Now remember, previously I say you will converge to Kesten-McKay law up in between -2 and 2. And now you assume that Kesten-McKay law is absolutely correct. If it's absolutely correct, then every time you integrate the density, and then you go to the I over n should be the location of the i's eigenvalues. Right? So if you believe that the Kesten-McKay is 100% correct, then this would be the location of the gamma I would be the location of the i's eigenvalues. I mean, because this I has a bit shift from it's actually has to be I minus 1 anyway. So I was. This I has to be I minus 1 because 2 becomes 1. We will just shift the 1. Okay, so forgive me about this. I didn't really normalize correctly. Okay. Now, if you take this as a definition, this is the correct location of the classical eigenvalues. Then what we prove is if you look at these eigenvalues from 2 to n, all n of them satisfy the following estimate. You say the lambda I minus gamma I with probability 1 minus n to the minus 1, basically with some small corrections. You will be lambda I minus gamma I is less than it's n to the minus 2/3 and times some tiny small corrections. And then this bound is start from entry minus 2/3, and then it keep on improving until somewhere in the middle. Once it's in the middle, we call it in the bulk, it becomes entry minus 1, because this I, when you look at this I, in the middle, this I is n/2, and the minima n/2 and n minus n/2 is the same order. So you can see that it starts from entry minus 2/3 and it starts to grow to entry minus 1. So this is accuracy. And this one, so you can establish for every single eigenvalue of them. Now, so there's there's a preprint immediately. I said this. I think Roman immediately told me that they estimate. Actually, the paper is also ready, and so what they prove is for the even d-regular graph with some slightly different models, and this lambda 2 bigger than 2 plus epsilon satisfies this bound. It's 1 over n of d divided by epsilon to the 8 and some poly log d and log epsilon. I should emphasize that this result is, I mean, they did many other results, and among their results, if you restrict to the d-regular graph, random d-regular graph, this is the result. And so if you take this this epsilon, it's about, I think it's n to the 1/8. That's a case of this general result. Restrict to this case. All right. So so now I will try to explain that why how we get this result, and also compare with the Erdős-Renyi graph case. So for the Erdős-Renyi graph case, our previous result was in last year, and it says if you take no, sorry. So here is the random d-regular. In the next slide, I will talk about Erdős-Renyi case. So we also prove that if the edge d can grow with n, so like n to the epsilon or even log n, then actually you find that the conjecture I mentioned previously actually was correct. It means if you take a second largest eigenvalues and then subtract the 2 times n to the 2/3, then it does converge to Tracy-Widom law. Right. So now let me go back a little bit just to show you what's going on here, because what was the conjecture? So here's the conjecture. The conjecture is for d bigger than or equal to 3, n to the 2/3 times this lambda 2 minus 2, subtract constant, converge to Tracy-Widom. So what we show is this conjecture is correct for d is not fixed, but it grows with n in some slow fashion, and then there's no correction C of d. So that was what we proved last year. All right, now so we call this this was the standard terminology is called edge universality. So edge universality is the probability distribution of the edge eigenvalues is independent of the probability law of the random matrix. And so this was edge universality. So I will always say universality means distribution of the eigenvalues is independent of the distribution of the metric elements. And now, so there's interesting corollary if you of this result. It says in the same regions, if you ask how many random d-regular graph are Ramanujan, actually it's 69%. But this 69% is because if you believe Tracy-Widom law is correct, now Tracy-Widom law you can compute what's the probability of Tracy-Widom law. It's on the left side of zeros, and then you have 2 eigenvalues, lambda 2 and lambda n, and you put it together. It's a 69%. Of course, it's simulation computing by using the Tracy-Widom law as what the numerator comes out. And now, but this result, I did this with many authors. This is just a result 2023. So previously we did something between 2/9 and 1/3, and there is previous work. We sort of emphasize on the small. The D is a small, but if D is large, there's also work by he on bigger than 2/3. Okay. Now, now the question is whether you can do this. You want to do this for finite D, and eventually you want to do this for D equal to 3. Okay. Now, now I promise I will say something about the Erdős-Renyi graph, and so let me just state the result for Erdős-Renyi graph. And then now you study, you can see the difference between Erdős-Renyi graph and this random deregular. You see that. Remember, Erdős-Renyi graph is the one each edge is selected independently. So this one has a lot more independence. All right. So what I say is, if you take random deregular, this Erdős-Renyi graph, and now you're asking the lambda I the i's eigenvalues, and now so the statement is you take lambda I, now you define the quantity called the chi hat. Chi hat is hij squared minus 1 over n. And now the chi is there's a random variable chi, which is the first term is chi hat. Chi tilde is chi tilde. All right. Now you take a lambda I minus L, and then there's explicit construction, which leading term is a Gaussian divided by square root ND. And now you subtract all this expansion term, then you will come to the Tracy-Widom. And this is correct for any D bigger than log n. And now you can see that if D is bigger than n to the 1/3, if you look at this, because the leading term is square root ND. So here is some numeric calculation. If you are very, very fast in arithmetic, you can see it. You can see that if D is bigger than n to the 1/3, which is my last sentence, then this term chi is smaller than the fluctuation of order 1 coming from the Tracy-Widom. And otherwise, if D is smaller than that, this term starts to dominate. So for the Erdős-Renyi graph, there's a transition from the actually there's a transition from the Gaussian to the Tracy-Widom. If you don't subtract this chi, then for D small, is Gaussian will dominate, and for D large, the Tracy-Widom will dominate. On the other hand, the result get to this conversion to the Tracy-Widom is because we complete identify everything. In a way, what our results say is all these random variables behavior up to the Tracy-Widom law, all the correction we just compute explicitly. And so the method did a lot of expansion, and but still, I mean, here we assume that D is bigger than n to the epsilon. And now why do we? And then there are people. That's because the Erdős-Renyi graph will start to decompose into component. But before it decomposes into a component, so you can see that there are truly a lot of works, and then later on this in 2021 this null, and also later on the extension by I'm talking about this slide. So they prove that it's going to a Poisson, but this is a completely different phenomena because this Erdős-Renyi graph is start to have many components, and that's why this kind of results become correct. All right, so I'm not. So this talk I will not say too much about this Erdős-Renyi. This is just I just put it here for a comparison, and so let's go back to now. For the rest of this talk, what I'm trying to I don't have a clock, so what's the? Oh, okay. So it's about, I have about slightly more than half an hour. So let me, I'll try to explain that why this kind of result is correct. And so, and this was, so let me summarize the first part of the talk. The first part of the talk is, roughly speaking, what he say is this, we obtain something we call the rigidity of eigenvalues for the random D irregular graph for D up to 3. And now, and then you can see that and then the main question is really you are trying to asking that whether this conjecture is correct or not. This conjecture of the second largest eigenvalue converge to a Tracy-Widom, whether this is correct. And this one, we know this is correct for D is n to the epsilon, grow with n, but we don't know whether, we didn't prove that this is correct for finite D. But for finite D, what we are doing, essentially, we are saying this n to the 2/3 times lambda 2 minus 2 is order 1. But we didn't prove it's order 1, we proved it's n to the epsilon. Or you can say we prove that this n to the 2/3 times lambda 2 minus 2 is log n to some power. Okay. So this was our main result. And now the next question is now how do we prove it? And so so for the rest of this talk, I will try to describe what's the idea and how we get to be able to do something like this. Now, so the first, this is a well-known definition of Stiger transform of probability measures. So you take a probability measure rho of x, and then you compute this Stiger transform. Now you can see that Stiger transform, if you compute the imaginary part of Stiger transform, you will converge to a density of rho. So that's the second line. Now, the Stiger transform of the semicircle law, you know, is the one, this semicircle, and it satisfies a quadratic equation is m squared plus z times n plus 1 equals 0. So this one is this exact calculation. If you compute this, you put into semicircle, that you find this is correct. Now, so for random matrices, always try to derive that this equation is correct for finite size random matrix. Now, Stiger transform of Kesten-McKay law is the Kesten-McKay has satisfied this relationship. So now this relationship of Kesten-McKay of z is equal to this minus z and minus d over d minus 1 and semicircle of z. So you can see that the semicircle, the Kesten-McKay law also satisfies a self-consistent equation. But this self-consistent equation it's actually a bit complicated because if you want to derive a self-consistent equation for Kesten-McKay law, what you have to do is you have to take this quadratic equation, and now in the next equation you solve the MSC in terms of M Kesten-McKay, and then you plug it in, and so this is how you can derive it. And now in the old days, what we are doing is this d, if this d over d minus 1 is 1, then the Kesten-McKay exactly becomes the semicircle, and then we just expand everything in terms of 1 over d. But then in terms of 1 over d, then you get the expansion, and then you have to check the self-consistent equation in the expansion of 1 over d, and it's kind of complicated. Okay, but in any case, in principle, there is a self-consistent equation. All right. Now, now next one is the green functions. So in everything we has been doing, we are trying to do the Green's function because try to, you know, when I start to work on this subject, and everybody was using the trace method, so we decided to try something else, and so this is what we try, and and now later on, the trace method becomes more and more powerful, and it's kind of interesting to see that two different methods give two different perspectives. Okay. Now the Green's functions is defined to be 1 over h minus z, and And then the Z is E plus I eta, and E is energy you are interested in, and eta is a spectral resolution. Now, the eta is spectral resolution. If you look at this, how it looks like. Now, if you look at the imaginary part of tracer Green functions, and now suppose the eigenvalue is at lambda I, eigenvalue location at lambda I. So now you can see the imaginary part of H minus Z is exactly lambda I minus E squared plus eta squared, and the numerator will be eta. And now, so this is trace of 1 over n. Now you look at this function, this eta divided by x squared plus eta squared. This is some sort of a delta function, approximation of delta function. So you can see that at AB lambda I, then now you start to see that there's something like that. Okay, so now, yes, everything is something like that. So then the width of this is eta, and now the width of this is eta, and so so something like this would never satisfy any self-consistent equations. So if the eta becomes bigger, then the distance of the eigenvalues of this start to become more like flat, and then this is something will satisfy the self-consistent equations. Now the distance between the two eigenvalues, is 1 over n, because your eigenvalue between 2 and minus 2, and you have n of them, and so the typical distance is 1 over n. So if the eta go below 1 over n, then you will see this random picture. So you're not going to see anything semicircle or whatever Kesten-McKay, just impossible. So 1 over n is considered as optimal scale. And typically, when people say they prove some, I mean, for example, like we're going to prove the semicircle law and so on. Now, usually, if you look at what they did, is they treat this eta equal to all the 1. All the 1 means you're looking at very, very large scale. And we call this a global law. And once you can do this for eta equal to 1 over n, then we call this a local law. So local law, it means that you'll be able to set this eta quite small. You will not be able to look at each individual one eigenvalue, but you can look at a few of them, and you can see quite precisely where they are. And so this is called a local law. And now, in our study of random matrices, this was mainly done with Erdős and Jin-In, and this was, I think, somewhere in the 2010 or somewhere around that. We realized that if you can prove a local law, and also the error bound is correct, then you imply the so-called eigenvalue rigidity. So eigenvalue rigidity is so what is eigenvalue rigidity? Is exactly this statement. Do I put it here? No. So eigenvalue rigidity. So this is the eigenvalue rigidity. So this estimate of the eigenvalues, the eigenvalue next to a classical location with all this entry minus 2/3, entry minus 1/3, all this will be correct. If you can prove that, this local law means you prove this, the difference between this one. I'll show you what do you have to prove. If you can establish this local law with optimal bound. But what do you mean by local law with optimal bound? Is this one. Is you prove that the trace of a green function divided by 1 over n, subtract the Kesten-McKay law of z, is divided by, it satisfies something look like that. The error term has to be 1 over n eta, and then also once the energy bigger than 2, it's a bit more complicated. Well, anyway, there's not. I don't think there's anything, but anyway, so it's this one. So it has to be. So in the bound it's much easier. In the edge it's a bit more complicated, but in the bound it's 1 over n eta. So if you prove this one with error 1 over n eta, and at the edge, it has to be something slightly, something, it's quite a bit more complicated. It has to be of this form. I mean, this one is the higher order to the matter, but the keys, this one has to be in this form. Now, if you look at this one, and then what's this kappa? Kappa is the distance to the edge. So kappa is distance to the edge. If you prove this over the edge, e bigger than 2, and inside you prove this arrow term 1 over n eta, and this will be correct for eta bigger than n minus 1. I think for the first reading, you should forget about kappa. It's roughly speaking, the arrow term has to be 1 over n eta. Once you have an arrow term 1 over n eta, then everything will be correct. So that's the idea. The idea is this estimate of trace of green function, once established correctly, with the correct arrow term form, and with eta up to 1 over n, then the eigenvalue rigidity will hold automatically. So this is the idea. So there's a statement about green function is so powerful that once you get this done, and then you prove everything. And now, in addition, if you look at if it's not just a trace, if you look at the metric element ij, actually our method also gives estimate on the metric element gij. In particular, even if we just look at the green function at the same point AA, even without as long as you don't take summation over A. If you look at the green function at the A of A, and now you write the green function into a spectral representation. So spectral representation, this means that there's the eigenvalues and there's eigenvector. Sorry, I mean this one is not particularly useful, and so I have to step in. And now uj of A squared. So the eigenvector of A squared. And now you can see that even if you show that this one is bounded, and now you see that, then you can see that uj of A squared is already bounded by 1 over eta. And now, now this is something very strange because it looks like there's a lot of summation. You just bound the summation. You just bound 1 over the term by the summation. But on the other hand, if eta is small, and once E is much bigger than, once lambda j and E are big, then those terms will be small, so you didn't lose too much. So you can see that even eigenvector, you can show the eigenvector is less than eta. And now, if eta is close to 1 over n, then you show that the eigenvector is less than almost 1 over n. But eigenvector less than 1 over n is the best possible because if eigenvector is completely flat, then this means uj of A squared is exactly 1 over n. So green function estimate tell you, if you can compute the trace, only the trace, it tells you eigenvalue correctly. And if you can compute the metric element, it actually even tell you about the eigenvector. And then it will lead to the eigenvector delocalizations. And it's exactly the statement. And this was what we did. We proved that the eigenvalue delocalizations also is done in this way. All right. So this is the about the green function, and so this is the key object we are using. Okay. Now, I still have more than 15 minutes. So so here is a list of a previous result, and there are a lot of results like that. So now about this random D-Log graph, I think it's you can see that people really try to improve this eta, this scale eta. You can see log n minus 1, log n minus c, and the various one. And so there are two results. I should mention this is not a fair comparison because there's anatharman and the Lindenstrauss. I think what they prove is something. I mean, it's something much more general because their statement is correct for the random graph with the local tree properties. So they don't need the randomness. So they don't need randomness. So this is not really a fair comparison. But I just tell you that I just tell you that this log it's quite commonly appear in various places, and so so this was the comparison with previous result with, but I think there are also some other previous I didn't list it here, and so all right now so finally let me just tell you a little bit about the ideas of the proof, because you know, it's I mean, usually in this kind of large meetings, people don't talk about proof, but you know, I'm a mathematician, so I try to tell you a little bit about proof. I mean, I can tell you more about introduction of random matrices, but I did it so many times. It's kind of all right. So now about the idea of the proof. So how do you prove this random d-regular graph? And because all the method we have, we start everything from random matrix. Oh yeah, but it's an upper bound. It just means we have a much sharper upper bound. We have much sharper bound, and their bound tend to get to just log, and so I see. So you're asking that what does this? Yes. So what I'm saying is the theorem says, for example, now this 2014 and the 2009, or this Van Woer's paper. Van Woer's paper is different. So when I say the scale eta is log n minus 1, what it means is that if eta is bigger than log n minus 1, there is a statement. They prove this trace of G and subtract something. It's correct. I'm not talking about even error bound. It's just the restriction of eta has to be bigger than this number. Yeah, the eta we have is eta is bigger than 1 over n. So there's a huge difference between this and 1 over n. That's the so. All right. Okay. So so now I'll try to answer Raman's question. And so if you look at random graph, then mostly it looks like a tree, and occasionally there are a few loops. Okay. And now so you look at the green functions. Green function, the most stupid expansion is it just expand like a geometric series. So now you can see the green function and trace method start to look the same. Just compute a polynomial, and now so this now you look at green function some of the weighted path, and now if you look at GOO, it's green function from O. So now it's a random walk from O and come back to O. So there will be two possibilities. One is from here, and then you come back to here. The other one is you come from here, and then you come back to the same place, come back. So the idea is it's actually this probability is quite small. If you want to, actually it typically come back to itself and come here. That's the most cases, and the reason is because you see the correlation function usually go too far away. It's tiny, and so these are the major contribution. So these are major contribution. Now you look at this one. This becomes random walk stuff from here, and you come back to itself. So it starts to become a self-consistent object. But this one and this one, there's a difference because this is coming from outside. It do not come back inside. And, you know, we do not count this part. So what you're doing is actually the following. So if you look at here. So if you look at this G, I, J, J, this means you take out, so you look at the J, but you take out I, you just cut off this piece. So I look at this object, so now you find that this one, you come here, and then it come back here. So this means at this vertex here, if I replace everything by Q, and Q is exactly the average of this object. So this is what's the average look like. And now you start to see the Q satisfy a self-consistent equation. It's this Gijj. If you average over these locations, this is called Q. And then this is the green functions of this tree. It's not tree, it's array. It's array with a Q at the boundary. So if you look at the green function of this object with the depth L, you call it y over q, you find the q will be similar to y over q. And then this is self-consistent equation we try to establish. And once you establish this is correct, then you automatically get this connection between the semicircle and Kesten-McKay laws and so on. So this one is intrinsic. It's not some. I mean, of course, I mean, it's because you are in the random de-Lagrange graph, but then this is what we view as a reason why there's a self-consistent equations. All right. So so now the solution of this equation is actually the semicircle law. So you prove that this one is semicircle law, then you automatically get a Kesten-McKay. Okay. And the reason is because here this is Gij, and then now you put back this missing vertex I, and then you become Kesten-McKay. All right. Now the other question. Let me try this. Okay. So anyway, this didn't work, but anyway, I can do it. So the other question is for random de-Lagrange graph, because if you work with random matrices, you know that this random matrix has for us we need a lot of independence, because once something is not independent, it's very difficult to compute its expectation. So now the way we generate independence is because even though random matrices are this random de-Lagrange graph is not independent, but there's something called a switching. Switching means if you take two edges like that, and now you become like this, then they are still the probability distribution are invariant under this kind of switching. So this become quite useful because okay, so because of how we waste some time, so I don't want to. So now this is the way we generate independence. We generate independence. We take a tree graph, and now we randomly select. So now there's this boundary edge here. So we randomly select for each edge. We select another randomly select one. So we randomly select many edges exactly paired with the edge, and now we start to randomly switch them according to a rule we talked about in the previous page. Then the probability distributions of these red lines will generate a random de-Lagrange graph. With original one, they are actually they has the same probability distributions. So this means, on the other hand, you can see that these red vertices are completely random. So from here, so we seem to generate lots of independence from nowhere. But this is really the symmetry of the problems. So from the symmetry of the problem, we obtain some independence, and this makes us to be able to compute this so that this metric B is essentially independent. And so this will makes us able to use lots of previous random matrix ideas, and then you can see that. So now I'm not going to go to details. So let me see. I still have 5-6 minutes, so let me try to finish the talk before the time. And now, so the idea was usually we use a Schur formula to compute the green function, compute the inverse, and then the Schur formula go like that. And now once this B is independent, and this will lead to a self-consistent equations, and this was the idea we was following, and of course so this one usually in a semicircle, this random matrix is this is how we get the quadratic equation in this way. This is a semicircle law. This was done in this way. Now in our case it's slightly different, but I think the key is really if you believe that this previous page, if you believe that that there's self-consistent equation of this form, then this is what the self-consistent equation is. Okay. All right. Now the next thing is oh, I see. The next thing is Now this one is a bit more technical, so I will not say too much. Is now how do we really dealing with the matrix before and after we do the switching, and there's a formula called the Woodbury formula. It's kind of useful, but anyway. So now now the idea what we are doing is so this is one more. Probably I just show you the word, and while we are doing the expansion, previously we say I take a random tree and then I random switch in the boundary, but this procedure actually we do it actually many times, because one random switch is not enough. So we want to explore a lot of randomness. So we do a random switching and do an expansion. We pick another term and do a switching again. So I'm now just talking about more like draw a Picasso. So sorry. And so you can see that we do expansion, and then we just take another edge here. It's even too small to really take another edge, and we expand it again. But anyway, so so this is not almost incomprehensible. And let me just finish by saying how do you do the edge universality. Okay. So right now, so far we just talked about how do you get estimate of the edge eigenvalues. But there's a question now: if you really want to identify the probability distribution of the edge eigenvalue, what do you do? Now, if you really want to identify the edge distribution of eigenvalues, so this is still actually so far essentially all the proof of this universality are depending on comparison and also depending on some sort of time evolution, some sort of dynamics evolutions. And this goes back to my roots doing particle systems, and so Professor Funaki must be happy to see it here. So if you look at the a random matrix, I mean, it can be random deregular graph. It doesn't matter what it is. Now you start to add Brownian motion into each metric element. I mean, here I use Onsen-Uhlenbeck, but you can just do forget about this one, just add the Brownian motions. Now add Brownian motion into the metric element. Now you ask the question now, how fast, after you add the Brownian motion into your initial metric, how fast the eigenvalue statistic will become like GOE. And then this is quite interesting question. The question is, so if you look at the speed to go to the convergence in the bulk, it's actually n-1. So you just waited for a tiny, very, very little time. It immediately becomes Gaussian. And then if you want to look at the edge, actually it has to wait a bit longer. But then you still just add a tiny bit of Brownian motion because time is quite small. Then you already see it immediately becomes the Gauss, the eigenvalue distribution becomes Gaussian. And finally, then you have to say that your eigenvalue distribution by adding this Brownian motion didn't change too much. And you put these two together, these two results together, they improve the universality. And this has been in all the proof of universality is basically from this kind of outlines. So I mean, it sounds a bit strange, but this is what it is. And the reason is because this convergence of eigenvalues, you're doing it not look at the metric structure. You look at the eigenvalue evolution, which was Dyson-Brownian motion. Okay, all right. So so now my time is up, and now so let me just do summarize by 2 pages. One is in this way, this is how we prove this for d bigger than n to the epsilon. We converge it to the we can carry out this for d bigger than n to the epsilon. And the reason is that we have a lot of expansion of 1 over square root d, and for fixed d, this starts to become a problem. And so so that's why we haven't done this for finite d yet. And now the last one is the summary of today's talk. Now we prove the eigenvalue rigidity. This means the order of fluctuation is the correct one for all the eigenvalues of random d-regular graph. And in particular, tell you the fluctuation of second eigenvalue is n to the minus 2/3. And the Tracy-Widom law was proved for d bigger than n to the epsilon. But the Tracy-Widom law is still open for d bigger than equal to 3. And now for the Erdős Rényi, there's transition at d equal to n to the 1/3 is from the Tracy-Widom to Gaussian. And we also proved the eigenvector complete delocalizations. And now, actually, there are other results about random matrices I didn't say. I chose to tell you more about the proof. Otherwise, one can also you can also understand the eigenvector statistics and so on. Okay, so thanks a lot. Thank you.
What do you mean by the Denote for the large species?
What?
The last page.
This page? The previous one? Oh, the previous one I didn't have time to. What?
The last one.
Ooh. Yeah, here. Oh. The noise dominating phenomena. This is something. What I'm trying to say is the following. So if you look at this, these two metrics. So when you say the time is very small, and then the eigenvalue fluctuations and so on, is already Gaussian. So this term is considered. This term is a noise, and the initial data is a signal. So because the solution of this one is original matrix plus a noise. So now for time very small, then you only see the eigenvalue becomes a Gaussian. It means your data, the information of data, if you look at just eigenvalue, information of data disappear already because what you see is just the noise. But here, this is correct because we are talking about a fluctuation of eigenvalue. We are talking about eigenvalue gap. The eigenvalue location will still typically follow this S0. But what we are saying is the distance between eigenvalue and all this final information will mostly follow the noise. You will not see the data. And so that's why this small noise tend to just kill the information buried in the data. And so that's why there are lots of papers talking about this. I think this Montanari was particular. He has really tons of paper, and also lots of this principal component analysis, and it is called this BPH threshold or something. It's also the same phenomenon. Yes. Okay.
I want to ask how to apply the categorical condition that the most of point has no cycle and the most of point has all the point has the small cycle. This condition to estimate the Stiegler's transform of
Oh, I see. So where does that come from? It's come from mainly because of this function YL. So you see that because this YL, we only consider case this is a tree. So once this is a tree, this one is very easy to compute. And then if you have 1 or 2 cycles, you can still compute. You can still compute this object. But once there are really many cycles, this becomes far too complicated, and you will not be able to compute it. So you need that. You need to be a sparse graph, and then just a neighborhood has to be more like a tree, or at least it has to be something close to tree. And once this becomes too complicated, even if you have this relationship, you will not be able to do anything because this guy will be just not. You cannot really. You don't really know what this is. Right now, this is a good self-consistent equation because you only have to compute this one for tree, and at most maybe one root. You just say it's a small probability and so on and so. So that's why it comes in here. Otherwise, this self-consistent equation, you can't use it. Thank you.